Claudia. Okay.
Ready.
Good morning to everyone. It's a real pleasure to introduce you, Giuseppe, for today's seminar. Here from these seminars from Severo Ochoa at BSc. We know each other for quite some time, and thanks to this Severo Ochoa program, he visited us some weeks ago here in Barcelona. His research is focused in structural integrity of composite materials, including fracture mechanics, computational modeling in this kind of materials, with experience with both industry and academia. He holds a PhD by the University of Porto with mechanical engineering through through the Marie Curie project called Momentum. He also worked at Alstom Transport as a composite expert, and he has been visitor in very renowned institutions such as AMADE at the University of Girona or NASA in US. Today, he's currently associate professor at the University of Enna, Core, in the center of Sicily, Italy. And with that, I give you the floor, Giuseppe.
Well, thank you very much for this kind introduction, and thank you very much also for providing the opportunity to visit BSc. I knew Barcelona, but I didn't know the center, and I really liked it, how it is structured. And it was, I think, a very nice and profuse experience. What we are going to talk about is today uncertainty quantification for a progressive damage model in a composite structure. It's, I think, a brief presentation, but of course, since we are not too many, feel free, to stop me, and if you have a question, even at the end, we can discuss in more detail some points. Okay, so let's see. Discuss as usual some motivation. The methodology that we propose will also demonstrate sort of validation that we have performed through some calculation, and also some conclusions, highlighting also the importance of HPC infrastructures, as you have there, and how HPC infrastructure can help actually developing this approach. I mean, in my case, which is computational mechanics, and focused on modeling fracture and damage of composite material, the approach worked. I'm sure that a similar approach might be also applied in different problems which have, more stochastic variables as input, and therefore, where uncertainty might be more complicated to calculate. Okay, so let's start with the motivation. I don't know if you all know what composites material are, but composites, let's say, are the evolution of the bricks made by the Egyptian, where they use the mud and the straw. Of course, we don't use mud anymore, but we use matrices or resins, which are thermoplastics or thermoset, 90% of the time thermosets, but the industry is moving to thermoplastics. And instead of the straw, we are using technical fibers. In this case, it might be carbon fibers. Now, these materials are inherently stochastic. And are inherently stochastic because the constituent, so it's not a material, it's a material system, the geometry of the constituent, the strength of the constituent, it is not, of course, a deterministic. I know that nothing is deterministic in nature, but in this particular case, we have a lot of variation. Also, the position of the fiber, the manufacturing process, how you or the operator lay, the apply down, all these introduce some uncertainty in the parameter, which are very difficult to control. More, we can say that composite material exhibits a very complex damage mechanism, or very complex damage mechanism, because you have fractures of the fibers, you have a fracture of matrix, you might have a plasticity, you might have the bonding, you might have the lamination, so the bonding of two adjacent plies. And also this damage mechanism changes, and their interaction changes with the size of the structure. So it's, of course, a very complex problem, which is affected by several random variables. And therefore, the randomicity, when you try to assess the structural integrity of a structure, and I have in mind complex aerostructure, needs to be taken into account. Stochasticity can be in everything. Mainly is in the material parameter and also in the geometry. Now, what we usually do when we start dealing with stochastic variables is to assume everything to be normal. This is normal, okay, this is okay. But let's say that assuming something to be normal might be sometimes a little bit, I used the word presumptuous. Maybe I could say, yeah, presumptuous, I think it is the right word. And that is why, because sometimes you have some physical phenomena where, okay, your variable is actually supported on all reals. So, okay, normal distribution can be assumed. But there are some variables, and probably all when we do fraction mechanics, that are not supported for all reals. You don't have a negative strength, you don't have negative Young modulus. So why assuming a normal distribution if you know that something might just be positive? Or if you have something like a Poisson ratio that you know is bounded between in a range, right? And this depends if the material is isotropic or anisotropic, but still is bounded. How you can assume something that is supported for all real? And more than this, it is not just assuming that something is wrong, is normal, but assuming something, it's actually very complicated. And it's very complicated because the actual underlying distribution is unknown and unlearnable. Is there. We make some experiments. Some experiments are the realization of these stochastic variables. But retrieving the actual stochastic variable, the actual distribution from few experiments, from few realization, well, probably is an act of faith. You assume something, but probably it is not so easy. Consider that certification in aerostructure is something extremely important and also extremely costly. So to certify a material, you need to run hundreds and hundreds of testing and to spend a lot of money. And even if you run all these tests, the number of data that you have are still a few. And assuming a functional form for your distribution, for your PDF from such limited data, okay, probably that might be presumptuous. I'm not a statistician, but okay, this is their approach I wanted to follow. So let's say that the distribution, the underlying distribution, are unknown and unlearnable. Now, what we usually do in computational mechanics. We use, of course, several approaches, but you can use a very simple analytical model. But when you want to do a complicated calculation, you use actual computational models. They take into account several damage mechanisms. They are based on a finite element model. They require resource-intensive infrastructure, so you require probably not Mare Nostrum, but something smaller, okay, that will allow you to run the model. Those are codes that have been developed through years of collaboration between research industry and academia, no? And can model several damage mechanisms. First time I wrote a ViewMat, which is a material model, no? I opened another ViewMat and I see that before me, 20 researchers given their contribution in different aspects. And I just added my bit, okay? So the thing also become mine, but probably in that ViewMat there are 30 years of research of different people. Now, there is some new research going on developing computational models that embrace or take into account stochasticity. So we are talking of stochastic effect, but that's not so easy. Probably it is the future. But I cannot say to the aerospace industry, to Airbus, to Boeing, that have invested probably millions of euro in developing these computational models that are very reliable and that they use to just abandon them and start doing something else. Of course, they can look into something different, but they are going to use at the moment this legacy model. Now, this legacy model are resource intensive, maybe are not, is not feasible to propagate error using them, because sometimes they might run depending on what you want to simulate, and of course depending on the HPC infrastructure that you have, in days or in weeks, right? So you might need to use a surrogate model, but I mean, is the effort put in developing a surrogate model always justified? When you develop a surrogate model, you simplify something. Is also this simplification acceptable? It depends what you want to model. So the question is that we usually have like two insurmountable challenges. One is the lack of knowledge of the underlying statistical distribution, and another one is the struggle, to define efficient and accurate surrogate models. So what if we could, for example, propagate the error and therefore calculate or compute uncertainty without assuming any distribution for the underlying stochastic variables, and also without the use of surrogate model, just executing the, I would say, original computational model? Is this something feasible? Well, this was the question that I tried to answer. And I have tried, I would say, to accomplish this through the combined use of bootstrapping and Bayesian analysis. Let's say, okay, we'll use what we have. We'll use what we have developed in years and what the aeronautic industry is using. But let's see if in this framework we are able to compute, uncertainty. So, bootstrapping and Bayesian analysis. Now, what is bootstrapping and what are the ingredients that we need? Okay, we need some experimental realization. So these x1, xi, xn there, those are experiments. Those are value of strengths, of fracture toughness, of young moduli that I have measured in some experiments. How many strengths I have? Maybe 20. How many fracture toughness I have? 10. This is actually coming from experiments, are raw data. And of course, I have also my legacy computational model that you have here. Now, what is bootstrapping? Bootstrapping is a statistical approach where you assume that the realizations of your stochastic variable, therefore the experiments, are representative of the actual distribution. And therefore, if you sample from the same sample, you might be able to represent or to maintain some characteristic of the actual distribution. It's not perfect, and after we'll talk about some little caveat. But what we will do is practically bootstrapping from all of this group and generate every time a input vector, which is originated by sampling from this different realization of the stochastic variable, running the computational model, the original computational model, obtain some prediction. The prediction are quantity of interest. It might be the first nonlinearity, it might be the peak load, it might be the onset of some subcritical damage. It's for you to decide what is your quantity of interest, and you run Bayesian analysis on this prediction. Bayesian analysis will allow determining some hyperparameters for your distribution. You will realize that at a certain point, this hyperparameter will converge. And when you will converge, it doesn't matter if you run 10, 200, or 2,000 more simulation. Because once it has converged, anything more you will do, additional simulation you will run, are superfluous. So the question is, can something like this work in computational mechanics and specifically for composites? How many simulations I have to run before the hyperparameters that model this the distribution of the prediction will converge? Okay, let's see. As you can see there, when we apply this approach, we are not assuming anything on the stochastic distribution, on the input distribution. I'm not saying anything on the fact that x1 is a gamble and xi is a normal and xn is a log normal. I'm not saying anything. I'm just working with raw data. And working with the raw data is actually what the engineers do. Okay, you receive a table, and after you start from this table of experiments. Okay, so we'll have this computational model, and we use what we, and when I say we, I say in this broad sense, as explained before, we have developed in years. It is able to model interlaminar and intralaminar damage, and also consider that the methodology that we propose here is agnostic. So it does not really depend on the model. You can use any model. I can use the model that is developed in another university. It is not the methodology linked to the model that I'm using. Bootstrapping, as I said before, it employs random sampling with replacement and does not require the knowledge of the distribution of the stochastic variables. And after we do the Bayesian analysis, so we formulate our probabilistic model. We need to condition this model on the observed data. We evaluate if the model fits, and we propose a posterior distribution. We need to start with an informative prior distribution, But a weakly informative private distribution ensure that the actual data do not really play a predominant role. Okay, so that's what we do. Now, in the paper that I could mention later, there are also some hypotheses that we made just to be sure that what come out does not really depend on the assumption that we make. Of course, you cannot always be 100% sure.
Sorry to interrupt you. Could you hide the rectangle, the small rectangle that zooms appear? Okay.
Okay. Thank you very much. Actually, I wanted to hide this from the beginning, but I didn't realize it was written hide. Thank you very much. Okay, so this is what we are doing and what we are trying to do and what is the approach that we would like to develop. Okay. Let's demonstrate some calculation. And we demonstrate some calculation with a test that is the standard on the industry. So it's an open hole specimen. So you have here a specimen with a hole. And what you usually do is you apply some load that might be tensile or might be compressive, and you determine your quantity of interest that it can be the peak, right? So we need first to define a material. And I've chosen this material here, which is IM78552, is a carbon fiber epoxy matrix. Is something I've used in the past. Now, but of course, it can be applied to any material. Now, what are the variables that you can consider stochastic? Several. Now, all these variables here that contain elastic properties, strength, fracture toughnesses, interlaminar properties are all parameters that I put in my model. Some of these are calculated because depends on other parameter, like in situ strength, for example. They also depend on the thickness of the ply. Others might be assumed to be stochastic. Okay, so let's assume, for example, to be stochastic, and the parameters that are considered in the model to be stochastic, but there is no limitation. You can assume everything to be stochastics, are the material parameters that are highlighted with a star. Also, you have geometrical parameters, right? And the play angle. So the geometry is highlighted there. So if the length of the specimen, Cx and Cy, that are the position of the hole, the diameter of the hole, the width of the specimen, and also the play angle. This is 0.90 plus minus 45 3 times symmetrics. That means 24 plies, and therefore we can also assume to have 24 misalignment angle. So if I go here, I could say that apart from the 13 material parameters, I might have also 3 geometric variables that can be assumed to be stochastic. Therefore, the diameter, the weight, the position of the hole. Some do not play a role, therefore are assumed to be deterministic. And of course, the ply mismatch angle. Since we have 24 variables, 24 ply, we'll have 24 variables. So if we take into account all these variables, we have 40 stochastic variables. So it's a 40-dimensional problem that we need to solve. Okay. So this how it is implemented. I've used Abacus, but anything can be used, right? Even Alia can be used to do this. There is a Python scripting that generate parametrical models of this, and I run it in Abacus, but anything. The question that arose there was, okay, but we also needed to validate this. And if the underlying distribution is unknown, how can I validate this? Because I think, maybe I'm wrong, but I think that the validation in the classical sense, like comparing prediction to actual experiments, cannot really be done because the underlying distribution are unknown and unlearnable. And also for the quantity of interest, that in this case is strength, we don't know this. And therefore I said here, okay, let's do this. I first play a god or nature. So I assume some stochastic variable. I assume some distribution. And I generate some data from that, sample from data, and using Monte Carlo simulation, I will build the distribution of the quantity of interest. Of course, it's a very demanding approach, but if you have an HPC, you can do this. But probably you cannot always do this for very large problem because you really need to run a very complex and demanding analysis. And after I say, okay, now I apply the structural engineer. And as a structural engineer, since I work on the raw data, I will just work on some data, assuming these are the experiments that someone has provided me. So if you see there, for example, this distribution, this is the distribution I think is a log normal that assume for the G1C, which is the intralaminar fracture toughness in compression in this particular case. But I do this for any variable, also for the geometric variable. And so the Monte Carlo simulation are run considering the blue distribution. So sampling from that. But after, when I apply the model, I apply the model only on the red crosses that are the data that as an engineer I receive. So this is probably the easiest way, not sure if it is the only way, to validate the quantification on the model. Okay, so I have some data that are fictitious that allow me to build through Monte Carlo simulation the output. And after I just take a few of these data and I apply my methodology, which is based on Bayesian analysis and bootstrapping. Okay, so that's what we have done. So what do? We run a simulation. For example, open hole tension or open hole compression, as you have here on the left. And you can have the quantity of interest that you want. There I selected the subcritical damage. So it's when you have damage in the matrix or the lamination. And also there is the first nonlinearity, and there is also the peak load. So these are some curves that are representative of some analysis. And what I do is I perform Bayesian analysis. I compute the the hyperparameters of my distribution. In this case, the hyperparameters are the standard deviation of the mean value. And as you can see, this high density interval that are represented there, they will show you that, yes, at the first simulation, I actually don't know where I am because the interval might go probably from 50 to 800. I'm talking of the plot that is on the top. But as soon as I run a few simulation, after 20 simulation, those hyperparameters are converged. And they don't move anymore. You can run even a 2000 simulation. You have frozen the hyperparameter. Same things is for the standard deviation. So a large standard deviation at the beginning, of course, this has to be just positive, and little by little, this standard deviation goes to zero. Again, around 20 simulations, which is feasible in any PC, and of course in any PC infrastructure, you get this. And this does not depend on the points that you choose to start with. So if you sample and you start with different red crosses, so you start to run this with different experiments, okay, because they provided you different experiments, actually the value that you get for mu and for sigma, for therefore for the expected values and the standard deviation of your quantity of interest are actually are actually the same. Nothing changed. I've run this hundreds of times. Just okay. Same things, of course. Here, I will not spend so much time here. So
sorry,
yes,
Giuseppe,
sure.
Just one question. I didn't get what OHC and OHT were.
Yeah, this is the OH is the open null, right? And you can run in compression, so the load is a compressive or intention.
Yeah.
So they are both used, and the curve is slightly different, because when you have like a compression, you have like this sort of softening, and there you have a little bit more abrupt thing.
And so the two graphs that you saw on the right hand side, OHT, are for tension only, right? That's what you said. Okay.
Yes.
Thank you.
So this is for OHC, and after for OHT. It seems the same slide, but actually they change, okay? So I did this Bayesian analysis for these two different cases. Okay, so thank you for the question. So what we have found with this calculation, repeating this calculation several times, that actually it does not really depend from how many stochastic variables we are actually considering, but after a dozen or 20 simulation, we actually reach convergent, and that additional simulation will not improve the accuracy of the prediction. Now, any functional form can be used for the quantity of interest, not just Gaussian. And you can perform the Bayesian analysis several times, because this is the easy bit. You run this simply in a Python script. The actual complex or computational demanding bit is running the original model. And you can also run, of course, statistical tests, Shapiro-Wilk or something different, just to assess the appropriateness of your assumption on the quantity of interest. But you do not assume anything on the input parameters, right? On the input to stochastic variables. So as I said, I repeat again, the time-consuming step is running the computational model. Bayesian analysis can be immediately performed in parallel, and you can do this for different functional form. And by sampling from the HPC distribution, you can get actually any statistic parameters, the entire distribution, a certain quantile, or, for example, what is very well renowned in aeronautic industry, the A value. And what is the A value? I'm making here an example. So the A value or A base value is the point on the left side of the strength first percentile that encompass the 5% of probability. So if you have a strength, what they will tell you usually in aeronautic industry is give me the B value or the A value. The A value is for critical structure. And therefore, in this particular case, it's extremely simple, because I know what is the distribution of my upper parameters. I can measure the first, or I can estimate the first percentile, and getting the distribution of the first percentile, and after determining the 5% probability on the left, and therefore getting the a-value. And the a-value is there for OHC and OHT. And again, now I can try to compare this prediction that I made starting from just a few data with the prediction that come from an actual Monte Carlo analysis. Okay, maybe it's a little bit confusing, but what do we have here? We have the results that come from different analysis on the OHC. The red one, A basis, comes from Bayesian analysis. So we have something which is about 370 megapascal. The other distribution come from a different approach, because I've also proposed a different approach in the past and are there. The black one, F1, which is this one, is what come from running the computational model in a Monte Carlo simulation. So just running a very demanding Monte Carlo analysis. I had the cluster available. It was a long summer. No one was using the cluster in Queens. And so I ran it, a lot of analysis. And what you get here, yeah, we have an error, but it's like 10 megapascal, which is nothing. 10 megapascal in the structural mechanics, nothing. Same things for OHT. Again, different approach. Here we were actually very lucky because we get exactly the same value. That doesn't mean that this happened always. It just happened in this particular case. But what you see there, all these different approach are actually giving you more or less the same value. And the A Bayesian, the A basis obtained with the Bayesian analysis is actually very near. In this case, is practically the same value of the true value that I generated through Monte Carlo simulation. The difference between all these different approach is the number of simulation that you have run. Because for the Bayesian analysis, you did the 20 simulation, not more than this. On the others, you needed to run dozen or hundreds of simulation, depending on the complexity of your problem. Yes, we just go through conclusion, and if you have a question, we can discuss at some point in details. So I think we have introduced a robust methodology for uncertainty quantification and progressive damage model for composite material. We have addressed the challenges of unknown statistical distribution of input parameters, using bootstrapping. And we have integrated this in HS, so high fidelity simulation. High fidelity simulation with bootstrapping and Bayesian analysis can reduce the simulation run, maintaining accuracy. Of course, this can be tested, and science is always like this. You need ways to test, to falsify, to apply to different approach. I don't say that this is the only way, but it worked with me in this particular case. We have applied this to a real-world scenario. 40 stochastic input variables showing high efficiency for industrial application and for industrial, we say, environment, which have HPC resource. We have efficiently estimated the hyperparameters of the quantity of interest distribution and demonstrated a very rapid convergence, usually, within 20 iteration. The model, of course, is the approach is, of course, model agnostic. It does not depend on the model you use. I use the computational mechanism for composites, but you can use anything. I think that for my small world or composites, this represent a significant advance on the uncertainty quantification, because allow you really to tackle very high dimensional problem in a very efficient way. And on the outlook, since I was in BSc and I'm talking to you, well, of course, HPC infrastructure will enable the analysis of, high dimensional problem, accounting for, in my particular case, different kind of damage and sources, and also will allow propagating error across different length scale, from maybe coupon specimen to full structure. This is something I cannot do, but probably you can do with the computational power that you have. And also HPC are important because allow you to validate some statistical approach, just performing very demanding Monte Carlo simulation, which will be infeasible to run without having this computational resource. Something that I did in a small scale with the very small HPC that I had available, but that you can probably do if you would like to test this approach for, in a larger scale. I mean, there are some more detail here. I have put this because I've also used this presentation in a conference of composite material. Here I've removed some probably boring information because wanted to give you, something a little bit more general that probably you can use also in your approach. And I think I have finished.
Okay, thank you very much, Giuseppe, for this excellent and really interesting presentation. So now we have some time for questions. So if anyone from the audience has any question.
Hello, can you hear me?
Hello, Adrian. I can hear and see you.
Nice. Thanks for the presentation, Giuseppe.
Oh, thank you for attending. I didn't realize you were there. Now
Yeah, but I had my camera off.
Okay, great.
So I was wondering, so if I understand correctly, because you don't want to assume any distribution on your properties of your model, you are using this bootstrapping technique, which samples the data from experimental values, right?
Yes.
And then what I was wondering is there any danger on doing this, in the sense that you are assuming that your data represents your real distribution
There
of
is
the material, no?
There is some danger, right? The first danger is that you might have, allow me to use this word, rubbish data. But this is something that happens independently. It is a risk independently on the approach that you are using, right? Because if you have rubbish in, you will get a rubbish out. So there is something that you have to fix at the certification level. Improve the experimental methods to get the actual property. We have had the experience of this. No, there are some material parameters for which it has been very complicated to measure the property. For example, interlaminar fracture toughness, that now is a standard, but DCB was like 20 years. It has been a standard for 20 years, but other things like MMB or ENF, they just were, let's say, certified or are part of ISTM norm by very few years. And there are other very important properties that we use. There is, for example, the intralaminar fractures. There are no test methods there is a test methods that I developed, but these need to be tested. There are the approach from people of other university. There are the guys in Imperial that do something else. There are the guys in Porto, the guys in Made, etc., etc. But you need to work on this. Apart from that, even if you have good data, there is another issue. The issue is that when you sample from data, this data will come probably from the center of your distribution. So with this approach, you actually can lose some information about details of your distribution. But this is something that you can also somehow taking into account because you can combine this with other approach. For example, in assuming the functional form of the quantity of interest, you may assume several, right? And therefore taking that one that is most conservative. Or also you can combine this approach with approach that are based on Fisher information matrix. So there are, in my opinion, approaches that will allow you, to get details. It's a problem because sometimes you get on the same material experiments that I've seen myself also because for some year I worked in industry, strengths, so something very simple, coming from one plant or from another plant, and they're totally different.
Yeah.
So the data that you get are heterogeneous, but this is something that can be worked on the statistical model. So taking into account, these details, but also on the actual testing. Because you might improve experimental protocols to avoid that. So it's not just statistic, or it's not just computational modeling, it's also experiments protocols.
I was wondering if you have very few experimental points, and for example, in your results you're showing, when you are bootstrapping your properties, how many experimental points do you have in your database? For a given property, let's say, just to get
in my paper, this is explained in the sense that I made several assumptions. For example, I show you here maybe. Okay. For example, for this G1C, which is fracture toughness intralaminar in compression, I have a 1, 2, 3, 4, 5, 6, 7, 8. Because usually this is what you have between 8 and 15, because this is a very peculiar test to perform. There are other properties where I have assumed to have more. For example, for the mismatch angle, okay, the mismatch angle, how you do? You do a CT scan of your specimen, and after you have an approach to somehow measure the misalignment angle. In that case, it's extremely easy from just one scan to get 300-400 values. There I have assumed a lot more. Strength, since strength is easier to run that fracture toughness problem, I assumed about 10 or 15 specimens. So I used my engineering experience to have some, I would say, reasonable data points to start with. But I'm playing as an engineer in a real environment. In a real environment, you do not have 600 data of strength. You have just 20, and you are lucky. Okay, so yes, that's
a problem. Okay. Also, then this is more like an open question. Okay, I'm sure you heard about something in statistics called the central limit theorem, which implies that maybe if you are sampling something from a fixed samples, like you are doing in this bootstrapping, and then with this sampling you do something else. Let's say I compute the mean of the experiments. you will converge to a fixed value. And when I saw this, when you are doing this Bayesian analysis, you converge so fast. It came into mind this. I mean, my question is, do you think this is taking some role in your approach or not? I don't have the answer, just an open question.
No, well, this is one of the most misunderstood statistical theorem that also took some time to me to understand when I was a student, but is actually very important. Now, the question is that I don't know how to answer to your question. What I think is that there are, of course, some simplification that we do and that actually we cannot do. I'm making you an example. Perhaps there is a relation between the strength and the fracture toughness. Okay, so this is something that if you read a lot of paper from this very important guy like Ricci, or also some preliminary paper from Suo, you can somehow see it, but it's extremely difficult to define. But when I run my analysis, I assume this variable to be independent. And actually, I cannot do this because probably all these variables that I have there are actually not independent, but depends one on the other, and I don't know how. And probably in that particular case, the theorem you mentioned that might not really work. But the question is, if with this Bayesian approach, I, at a certain point, reach the convergence of these upper parameters, it's like reaching the belief that things cannot change anymore. I think that it has some merits. Of course, this could be tested, and it could be tested also in problems or other nature, or in problems that have more and more stochastic variables. But this is something that, again, you guys could do there because you have the computational power of doing this. But yes, the short answer is I don't know to answer to your question.
Okay, thanks. And also just a very brief clarification. You mentioned a surrogate model, but I didn't understand what it was.
No, the question there is we can use surrogate models, right?
To replace the simulation, you mean?
Yeah, one of the approaches you know better than me is we use the surrogate model instead of our original computational models. Okay. Do some analysis, for example, Monte Carlo simulation, right? So I can, for example, use an analytical model based on finite fraction mechanics, for example, to predict the strength of an open hole specimen. We have the model, we have developed it using Python or MATLAB or whatever you want. It's something that give you the answer in a couple of seconds. And there, it's easy to run a Monte Carlo simulation. The question is that when you use finite fraction mechanics, you assume you don't have the lamination, you assume you don't have the plasticity, you assume several things that in your actual case, might not be really appropriate to assume. Therefore, yes, using a surrogate model introduces some simplification. Do you know if it is acceptable or not, the simplification that you introduce? Ideally, it is acceptable or it is not. You don't know because how you know? You needed to run also the original model to see if the results that you got are different. Therefore, it's something that you are introducing there that you don't know. Therefore, the question, the original research question was, okay, let's try to see if I can run a statistical methods on the original computational model, which is the most sophisticated approach that I have. But of course, in that case, you need computational powers and you need to reduce the number of simulation. And this can be done through bootstrapping and Bayesian analysis. But yes, you can run surrogate models because approaches that are, I've developed also surrogate model in the past, and approaches that are, in my opinion, quite promising, but also they require some understanding, are the methods that are based on multi-fidelity models, where you have the combination of a number of runs, a great number of runs of rough computation models, some runs of intermediate fidelity computational model, and just a few run of the very high fidelity computational model. There are some approach where you can combine this information, and of course you can run this in a reasonable amount of times, and you can predict the expected value and the standard deviation of your quantity of interest. Okay. So multi-fidelity approach works, but works because you have both the surrogate model and the high fidelity computational model. And again, these are my opinion that might be wrong. Someone can tell me you are totally wrong, but I'm perfectly fine with it. Okay. With being wrong.
Yeah. Okay. Thank you, Giuseppe.
No problem. No problem.
Is there any questions? Not sure if still we have time, Claudia, or yeah.
Yeah,
I would. I'm sorry.
Yeah, if there are more questions, we can continue. It's fine.
Okay, just one comment. Thank you very much, Giuseppe, for this presentation. It was very interesting. I'm familiar with fracture mechanics applied to composites. That's actually the subject of my doctoral thesis a long time ago. I was thinking, because you basically expounded something that is post my era of I was relying on theoretical analytical derivations to find relationships between some of the variables that you mentioned, but also in experiments. Some of the things that you can see when you run experiments, for instance, on toughness or strain energy release rate to derive those quantities, is that the distributions that you actually observe in your experiments are roughly Gaussians with fat tails. They can be biased on one side or skewed, if you like, but that's what you see. And in those cases, would just for these specific experiments where you know that the experimental empirical distributions have a certain shape, could you actually save yourself some work, still applying your methods?
Yeah,
but where you know that the distribution is skewed in such a way, and you never know where the actual peak or mean of the distribution is, of course, because you only rely on experiments. But could you save some time that way?
I don't know if you can save some time, because as you can see there, actually the number of the simulation of the run that we execute is not a lot. But probably knowing that we have a certain distribution, instead of saving some time, I can probably make our prediction a little bit more reliable. Because if I can really see a distribution, I can actually assume the distribution, as you said, and probably when I sample, I want to lose some information about the details that you will lose from bootstrapping. It depends on the approach, but surely you can bootstrap for some variables, and from other variables, you can just sample from assumed distribution.
Right.
Another approach you can do is, depending also on the importance of the structure, but you can also fit with a different distribution and taking the distribution that in your opinion is more conservative. You can also do this, but of course after that it will really depend on the philosophy that the structural engineer would like you to use. I think that if you have a lot of data and you assume a distribution because for some parameters is evident or is clear, probably there could make the model a little bit more reliable because you don't lose uncertainty on details. I've also to say that some parameters probably are extremely easy to see what is the distribution. Some others are not. One thing that probably was not, I don't know when you did your study in fracture mechanics, but one thing that is very recent, and when I say recent, I say like maybe 10 years, is measuring intralaminar fracture toughness. Now, when measuring intralaminar fracture toughness in the direction of the fibers, you have these fibers that breaks in bundles. So what you get is not a clear curve. You get like jumps. There, the fracture toughness that you get when you try to design your curve is actually very subjective. I made an experiment. I gave the same data to 3 different PhD students of mine. They brought to me 3 different curves. Because you need to, getting the information of the crack length, and this comes from an image, pictures, and where the crack is, you see here, and I see there, and after also these jumps in the load. So again, and probably this is connected with Adrian's comments, I think that we don't have to stop improving experimental methods.
That's correct. Yes. that's my take on my PhD, actually. Yes.
No,
thank you.
This is thank you for your question. Okay.
Okay, more questions from the audience? Okay, so I will do just a very quick question to you, Giuseppe. Do you see this framework scaling well with, let's say, higher nonlinear mechanical test, let's say for instance impact, because these open holes, no, at the end are non-linear, no, there is the damage model, also there is some geometrically non-linear on the behavior, no, we observe this at the close to the maximum load, no, this non-linearity, but most of the behavior is controlled, no, this non-linearity. But for instance, in impact, the non-linearity is much higher. Comes from the damage model, comes from the contact, comes from the interaction, no, between applies and
I think the same approach can be used. Of course, the problem you mentioned are much more nonlinear, but you are working on an approach that does not really depend on the model. It's something that I also wanted, to do, to apply the framework on some low velocity or ballistic impact, and also on crash worthiness, because we had some model, and I also worked on crash worthiness in the past, but never had the time to do this. The only things that you change, apart, for example, from increasing the number of stochastic variable, might be in the case of impact also adding some uncertainty on the load, right? Because, for example, imagine an impactor and something. Is it really perpendicular? Well, maybe it is not. So this additional uncertainty on the direction of the load, and probably also on its level, its entity, might allow you to get uncertainty for this particular problem. But I think it will scale well. This is what I proposed there, a 40-dimensional problem. So it's surely much more simple that taking into account an impact or an impact of a larger structure, but it is not a 2 or 3-dimensional problem. It's something that already has some sophistication. And therefore, I think that in case of impact, blast, or all these kind of things, it could work well as well.
Probably maybe the convergence that you have shown, no, with only 20 simulations of open hole were enough, no, the convergence. So probably in this, maybe in this high nonlinear, you would expect more simulations to conduct to
Yes,
get. No?
yeah. This depends on the specific test, on the specific problem. Because, for example, if I run an open hole tension, perhaps uncertainty will will come just from the strength and the fracture toughness intralaminar in direction one. In your case, you will have, if you do impact, also the fracture toughness strength in direction one will be, but also in direction two, you might have some delamination, you might have some plasticity. So the phenomena that will play a role in your particular case are more, but probably you will reach convergence within the 50 or 100 run. It's just to test it. Yeah, I wanted to do this because it was one of the interest, but one day I try. But I hope you will do before me so that I can do something else.
Actually, thanks for your question, Gerard. I'm thinking about the case where you have matrices that are not elastic, such as the epoxy or something like this, but plastic.
Yes.
Would you expect the same type of convergent behavior in that case?
Okay.
With a highly nonlinear response from the material, and in fracture mechanics, I would expect maybe something different. The mechanisms are obviously different, but
okay. This again needs to be tested. But what I expect is the following: even if the problem is highly nonlinear, because you are using some elastomers or thermoplastics or something which is not perfectly elastic, the variability and the uncertainty that you get in your response is it is taken into account in a very small step of the simulation. What I mean, okay, you have a nonlinear model, but the uncertainty that you have on a specific parameter is, okay, my curve ends here and ends there. but the problem itself might be linearized for that particular case. It does depends on the actual problem, but I don't see any problem in applying this approach. What can happen is that when you introduce a lot of nonlinearities and a lot of uncertainties, okay, you might probably get convergence later, but you would get convergence before the number that you needed to run for a Monte Carlo analysis. I don't know if I was clear. Probably was not.
No,
But again,
it's okay. Yeah, I understand. I follow you.
Again, no, I was not really clear there. But if there is something which is non-linear, the uncertainty will not really take into account the entire process or the entire phenomenon that you are modeling, but just a bit of it. And in that specific range, your problem might be linearized. So it depends actually on a lot of things, but I don't see why the approach might be used. It's just a matter of testing it.
I was thinking, actually, I was thinking a little bit on something different. That's not the last thing I want to mention.
Yeah,
that you might not have noticed because you don't know the people who, all the people, I think, who participated in this in the seminar. But some of us, I myself included, work in seismology. And in seismology, when you have a fault that is activated, you have typical of rough interface fracture mechanics or crack propagation. You have interfaces at the crack that are not smooth. And
Yes.
as the fault is activated, this roughness at the interface tends to get worn out by attrition. And so
Right.
along the whole mechanism of crack activation or fault activation, you have a major component of the mechanism that changes non-linearly all along the mechanism, and then the earthquake stops.
Right.
So
Yes.
it's not just a small portion of the mechanism or the process that can be linearized,
Right.
as you mentioned. And
Yes.
in this case, it's not that you don't know the distribution of surface roughness at the crack interface. It's that it changes all the time.
Yes. And that is clear. I understand that. Of course, I'm not really aware of that, but I understand something of cracks. And you have some intrinsic and extrinsic mechanism that can make crack propagation non-linear. You
Yes.
mentioned that there is a friction. We have, for example, same things in composites when we take into account the propagation of a kink band. So it's like in compression, and you have this friction or this attraction in this case that acts in all the crack, and that originate this arc curve. I don't know how you model that, and that is perfectly fine. But when you don't know what is the propagate value of the fracture toughness of your curve, probably is I don't know. I'm making number here, 150 Newton over millimeter, or 170 or 160. This is small variation, how it will be reflected in the model. Yes, okay, it's a totally nonlinearity. But within this small variation, perhaps the output, the answer that you get might somehow be linearized. So even if the problem is totally non-linear. So, but okay, again, this is something that needed to to be tested in your specific case is also, I suppose, extremely complex to run experiments.
Yes.
I don't know if you get experiments from historical data.
Yes.
But probably those historical data can be used. I don't know how, because this is something that I've never really reflected a lot, but could be used to bootstrap some data for your specific case and build the model. I know that a lot of people that work at the fracture mechanics now are working on seismology. Actually, Professor Rice, the inventor of J-integral, is doing this. And are still cracks, but at a very different length scale. But
That's right.
again,
That's right.
it's a matter of testing it. It's a matter, in my opinion, of testing it. But this is an approach that, of course, can be customized and it could be improved for a specific case. But I am probably a little bit naive here. I don't think why it shouldn't work, but I'm really naive, because the problem of this approach is also that you really needed to be a little bit of everything. So you needed to be an experimentalist, a computational guy, and a statistician, and so some things might not be entirely clear to me. And if there is someone that correct me, I mean, I'm here to learn.
Thank you. It's very nice to hear that you know Jim Rice.
Yeah, well, Jim Rice, you know that, well, and the close is Sicilian, because the mother is from Palermo.
Oh,
But
really?
of course, he went to, now I think he's in Brown, I think. Yes, and he does fracture mechanics of, some years ago, there was this crack.
Okay. Well, I guess that there is no more questions. Maybe we can conclude the seminar. Thanks, Giuseppe, and also thanks to all the audience for attending this seminar, and also the really interesting questions.
Yeah.
And that's all.
Thanks to you. Thanks for the invitation there. It was very, very nice. And thanks again, everyone attending, also for the very interesting and stimulating conversation that we ran after the boring presentation. Thank you. Thank you very much.